So the U.S. has an Inflation Reduction Act, and what it calls for over the next several decades is reducing emissions relative to historical emissions. By 2035, all of our electricity in the United States will be from renewable energy resources, dominantly wind and solar. By 2030, 50% of all of our new vehicles will be battery electric, and by 2040, 100% will be battery electric. That's 8 million vehicles in 2030 and 16 million in 2040. There are only a finite number of pathways to get us to what we think of as carbon neutrality or net zero. One of them is electrify everything. Everything that we do, minus flying, will be electric, which is going to require that total electricity increase by at least a factor of 3 or 4 or as much as possibly an order of magnitude in a really short amount of time. When we look at wind farms, everybody in the room sees all of the elements in the periodic table that are required to make them. Similarly, when we look at solar panels, everybody in the room sees all of the elements in the periodic table that are required to make them. And we know that all of these elements have to be mined. In fact, we can no longer say if it can't be grown, it has to be mined, because everything that we grow is grown with fertilizers that we mine. When we think of battery electric vehicles, most people in the general public commonly think of them as just lithium-ion batteries. But lithium-ion batteries and battery electric vehicles also require copper, nickel, manganese, cobalt, rare earths, and other metals. If we look at the elements shown here on the periodic table, where the colors indicate pink for wind power, green for electric vehicles, and blue for solar photovoltaic, we can see that the demand for what we think of now as energy critical metals is going to increase significantly if we move towards a world that is fully electrified. When we think about electricity, the fundamental metal is copper. It's like the arteries in our body that carries current throughout an electrified world. So even though in the United States, our Department of Interior does not classify copper as a critical metal, the ability to electrify everything in our lives hinges on our ability to mine the amount of copper that we need to electrify everything. So what Larry and I have done over the last few months is we have followed a similar methodology as Simon Michaud and a couple of others, Dan Yergin, and we have calculated the total amount of copper required for multiple scenarios. And I'm going to walk you through graphically what the results look like. So first, if we look here at this plot where we have annual copper demand on the y-axis versus time on the x-axis, total demand in 2018 was 23.7 million tons of copper. The curve here for the non-energy transition demand is based on Dan Yergin's work. And what that curve is for the nearly 4 billion people around the world who don't have access to electricity 24/7, 365, and the 1 billion people who have zero access to electricity. If the entire world achieves a lifestyle that those of us in the United States, Canada, the European Union, Australia, were blessed to be born into and on average take for granted, that's the demand for copper over the next few years to achieve the UN Sustainable Development Goals for the entire world. We modeled the growth of all automobiles, including motorcycles, and the dip here is because of COVID, but we assumed a growth rate for vehicles in China of about 3% per year, a growth rate for vehicles in the rest of the world of 2.5% per year, and we didn't assume any significant change in the growth of vehicle consumption in the United States and the European Union. But you can see that the number of vehicles are going to increase significantly. Right now, the entire continent of Africa has 60 million vehicles. That's going to change over the next few decades. So now what I've plotted is the calculated copper demand for several scenarios. So at the bottom here is the copper demand, the lower line, for the non-energy related transition, right? That's for the entire world to have the lifestyle that I have. And then as we move from bottom to top, the green line is the amount of copper, the additional amount of copper that we'll need to increase and improve transmission and distribution of electricity globally. Then as we continue to move up, we look at three different scenarios for electrifying all ground vehicles. The bottom blue curve is nuclear, so that assumes that all of the vehicles that we drive are electric, and all of that electricity is produced by nuclear power plants. We then used the mix of 2018 electricity production technology fuels globally to calculate how much new copper is required if all of the electricity for electric vehicles is provided by that 2018 mix. And then we calculated how much copper is required if all of the electricity for all of us to drive battery electric vehicles is produced by wind and solar. And you can see that we go from current demand of about 23 million tons to a demand that's pushing 60 million tons per year by 2050. If you look at the entire world, and we imagine a world where there is zero combustion of fossil fuels, and all of our electricity is produced by wind and solar, that's the top line. And you can see that in that scenario, total copper demand increases by a factor of almost 7. So a question is, can we mine it? We're used to the IEA and lots of agencies telling us that copper demand is going to increase by X amount over X number of years. So what Larry and I did is we used the Hubbert method when Hubbert in the late 1950s calculated peak oil. And it turns out that it's a relatively straightforward methodology to calculate what we call peak copper. So plotted here is global copper production and demand, and I'll show you demand in a few slides, versus time again. The red squiggly line is the actual global production per year since, we started in 1900. This is by 2000. And the solid red line is the mathematical prediction of mine copper production in every year, shown here from 2000 projected into the future. And it turns out that all you need in order to do that is you need to plot annual production divided by cumulative production versus cumulative production. And the slope of that line and its x-intercept, that tells you what peak production will be, total copper on the planet. It's relatively straightforward. And we modeled that starting in 1900. So the red solid line is the prediction, and what you can see is that the prediction almost perfectly matches annual mine production year over year. We then modeled refinery output. So refinery output equals mine production plus recycling production. And for recycling, we assumed a constant growth rate over the next several decades. And again, come to our poster for those details. And you can see that both mine production and refinery production peak in the year 2086. And in 2086, peak mine production is about 46 million tons of copper in that year. And refinery production is about 61 million tons in that year. If we now add the demand for these multiple scenarios where we electrify everything, the first thing that we can see is that for all of these scenarios, mine production and refinery production will not provide enough copper. It just won't. If we then model the top line here, wind and solar, assuming that there are no fossil fuels used in the United States and the European Union, only those two regions. The rest of the world can keep using fossil fuels, including China. That if the US and the EU completely electrify and all of our electricity comes from a combination of wind and solar, we need on the order of 67 million tons of copper per year by 2050. Right? That's 3 times current annual mine production. We then looked at how much copper we think can be produced if we take into account all of the currently operating major copper mines globally. And first, I'll show you that in order to remain on this Hubbert copper curve, we need by the year 2040 to mine about 31.3 million tons in that year. So mined copper production has to increase by 50% in roughly the next 15 years. To put that in perspective, the Resolution deposit in southern Arizona, if it goes into production, will produce 500,000 tons per year. So we would need somewhere on the order of 20 resolutions to be put in production every year for the next couple of decades, just to stay on that curve. So if we look at the top 10 copper producing mines in the world, and we take an average production on the bottom, the average production is just under 500,000 tons per year. All right, that's the average of the top 10 producing mines on the planet right now. And what we then did is, for a variety of scenarios, to remain on the Hubbert curve, T&D is new transmission and delivery, everything electrified, electric vehicles, and all of the electricity from nuclear power. And then if you go down to the bottom, that's the world where there's zero fossil fuel consumption by anyone. Everything is electric. Cooking, heating, air conditioning, ground transportation, everything is electric. And we built in 4 weeks of energy storage, grid-scale energy storage, using lithium-ion batteries, and the copper required to produce enough lithium-ion batteries to store energy for 4 weeks globally. Then we need 6.5 of this average, 6.5 of these mines to go into production every year until the year 2040. It ain't gonna happen. So now I've added to this graph the number of mines for each of the various scenarios. And I'll finish, because I want to leave some time for Q&A. I'll finish by making what I think is the most important point here. Most people in this room think that it's sort of our ethical and moral imperative is to electrify everything so we can mitigate our impacts on global climate. When we think about our ability to buy copper at whatever price copper costs, and we think about the 3 to 4 billion people around the world who don't have the income to buy copper if it could possibly be $4, $5, $6 a pound, then the prediction is that over the next couple of decades, everybody in this room from a more developed country is going to drive an EV. I have one. Everybody in this room is going to see growth of solar panels and wind turbines. Home energy storage that's lithium-ion batteries or lithium iron phosphate batteries. We're going to improve the transmission and delivery in the global north. And what that is going to do, ironically, is it's going to increase the economic divide between the global north and the global south, which is the antithesis of the UN Sustainable Development Goals. So as we think about electrifying everything in the global north, we have to think about it through the lens of, is it actually possible to mine that much copper? The answer is no. It's just a flat out no, it's not. We can want the answer to be yes, but it's one of these truths that whether we like it or not is absolutely true. We cannot mine the amount of copper to do what the stated policy scenarios tell us we want to do. And if we want to develop the currently less developed countries of the world, then we have to think about how we properly allocate copper so that everybody in the global south can get closer to the lifestyle that I've taken for granted for my entire life. Thank you.